Hello friends. So in this video we'll continue our example of virtual address to physical address. So suppose our logical address, that is the virtual address. Logical address, another name is VA also, that is virtual address. Suppose it is given as 6 and my page size is 4 bytes, right? And then from this logical address I need to get my page number and offset. Then only I can proceed with my explanation. So P equal to then P we can find out from logical address by dividing the logical address by page size. Because of that it is given, and it is your integer division, that also you need to remember. So 6 by 4, your answer will be 1. So your for this logical address 6, it will be there in page number 1. And then your offset will be logical address modulus page size, that is 6 modulus 4, answer will be 2. So see here, this is my logical address space, this is 6, see here properly, this is 6. So this address 6 is there in page number 1, that also we have got it here. See, this is page number 0 where the first 4 bytes are there, then the next 4 bytes are there here. So see, in page number 1 we'll get the address 6. We understand that. And see, in page number 1 how far it is located. This is 0 offset, this is 1, this is 2. So see here in page number 1, if I know the beginning of my page number 1 and I go 2 steps down, then I will get my actual logical address 6. So from this logical address 6 we have retrieved page number and offset. This part is fine. Now we need to know where it will be there in the main memory. So for that, what we require? We require our page table. And in the page table, where do I see? By index 1. This is my index. So I'll see at index 1. At index 1, what is there? Frame number given is your 2, right? So in frame number 2, it will be there, right? So see, here in the page table, the 4 pages belonging to the process are there anywhere in the memory. Page number 0 is there in frame number 5. Page number 2, page number 1 is there in frame number 2, and then page number 2 is there in frame number 1. So it is here. Then page number 3 is in frame number 6. So they are anywhere in the main memory. Now I'm coming back to my example. So see, for page number 1, the frame number is 2. So here it is frame number 2. And inside frame number 2, where is your offset? Offset is 2. That means what? If I know the beginning of my frame, then at offset 2, this is 0, this is 1, this is 2. So this 10 is the physical address corresponding to the logical address 6. So where from I'll get this 10? First, I need to get the base address of my frame number 2. How can I get that? If I know it is my frame number 2, when I reach frame number 2, before that, how many frames I have traversed? Frame number 0 and frame number 1. 2 frames I have already traversed. And in each frame, how much I have traversed? 4 bytes, right? So see, this how we will write page table and index number 1, whatever frame number will get. So this is my frame number 2. So that I will multiply by my page size. That will give me what? The base address of my frame. That is nothing but 8 here. Because PT1 means page table at index 1, what is there? 2. 2 into 4 is what? 8. So this is my base address. With that, I will add the offset 2. That means 8 plus 2 is 10. So this is my entry. This is my corresponding physical address. So for this logical address 6, this is how we can generate the physical address. Only one thing you need to remember, we should know my page table content. Then only it is possible. Otherwise, how do I know where my frame is given for a particular page number, right? So this process is clear. Now see, if I am talking in binary about the addresses. If I talk about the addresses in binary, then see, this logical address is what? 6. How can I write 6 in binary? I can write binary 6 is what? 110, right? 110 is 6. This much we know. And see, page size is 4 bytes. Now see, this 110 is divided into 2 parts. One is offset, one is page number. Now see, what will be the size of offset if the page size is 4 bytes? 4 bytes means what? 4 different locations are there inside a page. So to identify one location, we require 2 bits. 2 bits will give me 4 combinations. So lower order 2 bits will represent what? Offset. Then the next higher order bits will represent what? Page number, that is P, right? So here from 6 in binary, I got this as my offset and blue color is my page number. What I will do next? Add this number in the page table will index. So this 1 is indicating what? Numerical 1 also. So next see, my P is 1, D is 0, my D is 1 0. D is not 0 1, D is 1 0. Huh? This is 1 0. Then next you see, then what I will do, my physical address is PT1. PT1 means this entry 2. 2 means what? 1 0. 2 means 1 0. And what is my offset? 1 0. So it is 1 0. So as a whole binary, my answer is 1 0 1 0. What is this 1 0 1 0 represents in decimal? 10, right? So that is nothing but see, the decimal of this particular address is what? 10. So here when I did this method, I got 10, and if I did in binary, I got this 1010. So this is how we arrive at a address. And see where from I got this 2, because PT1 contains what? 2. So 2 is in binary 10. So with this frame number, I have combined my offset, that is 10. Here I did one mistake. This is 10. Huh? While writing in the slide, it was wrong. So as a whole, my physical address is 1010 for the given logical address. Hope this part is clear. In any of the methods you can do, whichever you are preferring, in this method or this method, any method you can do the address translation. Hope this part is clear. Then the next we will see that how to make my address translation process faster. See, actually whenever we are using the concept of virtual memory, the benefit part is what? We are getting bigger size memory than the actual size of your main memory, right? That we know. But in this process, whenever I am accessing one data, suppose from this address 10 only I am getting one data. So to get this data, I am referring to the memory twice. Once for this 2. Where is this page table? Page table will be there also in the main memory. So once I need to access the page table, then from there I'll get the frame number. Using frame number and offset, I'll get my address. And from this address, I will get the data. That means what? In this whole process of virtual memory, whenever I am making a memory reference for one memory reference, I am referring to the memory twice. So what it will do? It will make my process slower. Though I am increasing the degree of multi-programming, but it will slow down the whole process. Why? Because of that slower memory accesses, right? Because memory accesses used to take much more time than the processor operations. So, and here what we are doing, instead of one, we are referring the memory twice. So again, we are taking more time. So now what I will do, or what we need to do is, we need to reduce the time that is taken in my virtual to physical address translation process, logical address to physical address translation process. So the basic idea is what? In your page table, there will be so many entries. Here I am showing you only 4 pages just to make you understand the concept of translation. Suppose in my page table, say 1K entries are there, or more than that are there. But what I know, if from my page table, only few entries I'll be using most frequently. Only few pages I'll be referring more frequently. So what I will do, the all those entries we will be copying into one high speed memory, right? That is nothing but cache memory. So whatever number of processes are there in my system, for each of the process, whatever entries of their page table we are referring frequently, all those entries will be copied into one another higher speed memory, that is my cache memory, and there I will keep it. So see, another bigger point you need to observe here is page table is a per process concept, but the faster memory where I am copying the page table content for process 0, suppose these 3 4 entries are there, then process number 1 some entries are there, then process number 5 some entries are there. So the point is what? This is a global data structure. Here we are copying the page table entries of all the processes whatever we are executing currently. Their most frequently used entries of the page table will be there in this global data structure, right? That is there in this concept. But the beauty of this concept is whenever I am referring to a particular page, then I will try to find out that page here. If I get the page number here, then I'll get the corresponding frame number. From there, I'll get the data. Then I need not have to refer to this slower main memory for the page table. That is the beauty of this method. So see, now again I'm going to start paging with TLB. So with paging, to access a byte from memory, we need to refer to the memory twice. Firstly, for what? The first access is for what? To get the page table. Not get the page table, to get the frame number from the page table. That means to make a reference to the page table, we are using memory once. Second reference will be to get the byte or the word that we are accessing from the generated physical address. So for one particular access, we are accessing the memory twice. So thereby we have increased the time. Now our idea is to we need to reduce this time. So to overcome this slowdown, a small first lookup hardware cache is used, and that is called as translation look aside buffer. See, the entries of my page table will be copied into a cache memory, and that cache memory portion is called as translation look aside buffer, because that particular portion of cache memory is used only in the process of translation from virtual or logical to physical address. So translation look aside buffer, first I look into this buffer, whatever portion, if I get the frame number there, then my translation process will become faster. Why it will become faster? Because I need not have to refer to the page table stored in the main memory. Rather, I will refer to what? Only to my cache memory portion. So thereby I'll get my frame number quickly. From the frame number, I will get my physical address and I'll get the data from the memory, right? So this how we are going to do, and then next I'm going to explain at greater details the concept of TLB. Till then, thank you. Hope you are getting from explanations. Next we'll see the TLB concept in my next video. Thank you.